Now, there are some particularly useful ways that you can employ factoring to deal with expressions that contain squared values, that is, values with an exponential of 2.
For example, suppose we need to subtract 4 from x squared. Well, 4 is the same thing as 2 squared, so we could rewrite the equation like this. Now, to subtract one square from another, you can use a technique called the difference of squares and refactor the expression like this, removing the exponentials. A perfect square is the product of a number multiplied by itself. So for example, 4 times 4 is 16, so 16 is a perfect square. Now look at this expression, which includes a variable x and a coefficient and a constant, of which 3 is a common factor. We can refactor this expression like this: x plus 3 times x plus 3. Now that's a number multiplied by itself. In other words, it's a perfect square. So we could rewrite this like this: x plus 3 all squared. There's a general formula for refactoring perfect squares in this format, and it's worth memorizing this. You'll find it useful when you need to solve quadratic equations, which we're going to cover later. Let's just run through an example to prove to ourselves that it works. In this case, we'll use a value of 2 instead of x for a, and we'll leave the b value as 3. 2 squared is 4, 3 squared is 9, and 2ab is 2 times 2 times 3. We can easily work out that 2 plus 3 all squared is 5 squared, and 2 times 2 times 3 is 12. Now remember our original equation? X squared plus 6x plus 9 was refactored as x plus 3 all squared. So the a component was x and the b component was 3. With an x value of 2, x squared is 4 and 6x is 12. So you can see that the formula holds true. And of course, with known values for both a and b, we can finish off both sides of the equation and see that the two expressions are indeed equal. In this case, our perfect square turns out to be 25.